Okay, so this is an instructional video on how to do the force table. All right, so you have this simulator, and it has a simulated force table, which is just a circle. I get that it's just a circle, but it has three vectors that have to have a magnitude and an angle. That angle is always going to be measured from this positive x-axis. So no matter what angle you get, it's measuring it from this starting point on the positive x-axis to whichever way that the vector is going. We'll break it down into some more manageable angles, but you'll see that in a second. If this looks like the same one you have, you can always just hit the red button for click for a new vector, or if you get confused on one, you can do that, but it will start everything over, including what you need to put in these sections, okay? Now, this little circular thing is a tool that you can drag to exactly where you need, and it'll show you your angle. So let's do that for the first one. And I will admit that it's kind of difficult. You want to try to line it up. I go a couple of different times and I see what one degree back and 1 degree forward does, and normally I can decide on just the angle I'm going to put it at. All right, so I decided on this one was 81 degrees, and so I copy that down, 81 degrees at 276 newtons of magnitude. After I measure each one, I go ahead and then start to break it down into its component parts. So I draw it out just for me to see. This is that same angle. I know that it was 81 degrees, 276 newtons. I'm going to call this A just so I know that it's my first vector, okay? Vector A, all right? I then need to break it down into vector AX and vector AY component parts. You can do that with sine and cosine being multiplied by the hypotenuse. Will give you that of the angle. Put all your values in, you get a value for the y and a value for the x. Notice this would be positive for both of those. Goes to the right and up, right? So leave those as positive values. This little marker is just if you're using a graphing calculator, you're going to have 6 different numbers that you got to add together. So I like to go ahead and I round it for my paper, but I keep it in my calculator. So I stored this one as A and this one as Z. I'm going to keep all of my Y's as ABC, all of my X's as XYZ. Okay? Might help you too. Then we go to our next vector, right? And these are force vectors, but I just called them vectors for this time being. And so lined it up again. This gives me 107 degrees. Remember, that's from this, right? It's 495.4 degrees, 0.4 newtons of force. And I can then break that into its component parts. So I draw it out. No, this isn't to scale. It doesn't matter if it's to scale as long as it's in the same general direction and you have the number values that you need. Notice that I drew this angle here because that's from the positive x-axis. But when I'm drawing its vector components, I'm going to want this angle. I know that these together have to equal 180, so I just did 180 minus 107, and I got that this had to be a 73 degrees for the angle in our vector B. Okay, now that's 73 degrees from the negative x-axis, but it still works for making our right triangle because we need it to figure out these component parts. Remember, this angle really is just so you understand where it is and you can break it down into its component parts. Use sine and cosine function again. I get my vector in vector B in my y direction. And notice that this time I go ahead and mark my one in my x as negative. This is in the second quadrant, so x value should be negative. That'll come in a minute. You won't have to use it all the time. Remember that negative just indicates direction. Again, I put reminders. I stored this one as B in my calculator, this one as Y in my calculator. So these are just rounded values that you're seeing on the paper. Third vector. My third vector is all the way down here in the third quadrant. I'm going to call it VC. It's 259.7 newtons, and it's at 206 degrees. Go ahead, draw that out. Notice I just roughly draw it, calculate my regular angle that I'll need for my component parts based off of the angle they give me from the positive x by subtracting that from 270, which would give me 3/4 of my circle. And so it gives me an angle of 64, and that's what I'll use for theta. Notice that both of these are going to be negative. Your y is downward, your x is to the left. That would make sense for something that is in the third quadrant of a graph, right? Use trig to figure out these and get them down to their base points. Your trig won't give you negatives most of the time, so I go ahead and I put the negatives in, and then I store them in my calculator. Okay, now that you have all of your component parts, you do that simple vector addition you learned before, where all of these added together will give you a resultant vector, right? Well, you need the component parts because you can only add things that are in the same direction. So all of my x components and all of my y components I can add. So I put all of those. That's why I needed them in the negative value, because it's going to change greatly your resultant x and y depending on if you put those negatives or not. I had 2 negatives in my x's and only 1 positive, so I ended up with a negative x resultant. And I came up with a very big positive for my y resultant. Okay? You then draw those out from tip to tail. Remember, x was negative, so I draw it going to the left. And then from the tip of that one, I start the tail of my y one, and it was positive, so it went up. And then I connect the tip or the tail to the tip, and I have the direction my resultant should be in. This is a right triangle, so I can use Pythagorean theorem, which is a squared plus b squared equals c squared. Solve it for c. You just get the square root of a squared plus b squared. Now I make that fit my angle, so I'm going to use square root or the squares of rx and ry, square root of all of that. Put all of that in. I get the resultant magnitude. Notice it's a magnitude because this isn't going to give you any negatives. It doesn't matter if it's negative here. As soon as you square it, it's going to be positive. It's going to give you the magnitude of the resultant vector. Now, here's the thing. We don't want just the resultant vector. We want an equalizing vector. We want one that would stabilize all this. So we want it equal in magnitude, but opposite in direction. So this magnitude works because this is the magnitude of not only the resultant vector of all three of these, but it's the amount of force we're going to have to apply in the opposite direction of all of these in order to neutralize it. So this is our big magnitude. So I'm going to go ahead and circle that in white because that's what I need for part of my formula. The other thing, I'm going to need an angle. To find my angle, to find my angle, I'm going to break this down a little bit more. So I can use my simple tangent of theta is equal to opposite over adjacent. I move tangent by doing the inverse. So inverse tangent of opposite over adjacent is equal to my angle theta. Remember, this angle theta is really just going to be right here. This is where theta is in ours, okay? Because that's what will give us our component parts. Now, if I plug in my ry over rx, that's my opposite side over my adjacent side of theta, and I do my inverse tangent, I'm going to get the angle 62.1 degrees, right? So that's what I got for right there for my theta. But I don't want that because that is this angle. This is the resultant angle of all of these that are together. So this is my r. Well, let's write that again. That one is my r vector, my resultant vector. I want an equalizing one. My equalizing one will be the same magnitude but going in the opposite direction. And so I just need to add 180 from it. Well, first of all, I need to figure out what that resultant was from my positive x. So the first thing I have to figure out is that portion right there from positive x. do that by subtracting it from 180, and I got that it was 117.9 degrees. That's how much that one is from its origin point, is what I did there. And then I added 180 so I could get the equalizing vector. So I just add 180 to that, and I got 297.9 degrees. Well, that's going to be the angle that I then need this magnitude up here for in order to get an equal balanced vector. That should give me 0 for absolutely all of it. I plug that into my formula, or into this here. So this is the table. There's my 715.8. I think that was what I actually had, wasn't it? I lost my sheet now. Yep, 715.8. And then I got that it was 297.9. I hit check your answer. It checked it off and said, yes, you are correct. Yay! Now, it had rounded values that were slightly different. Look, that's super close to that. That one's off by a couple, but it just means they rounded somewhere along, and it was smart enough to know the difference, okay? So that is my resultant vector, or my equalizing vector, right? It's the missing force in order to make this table sit still, all right? And that's how you do those. I hope this helps.